Brijitta Joseph Bonafis to present her talk. Thank you.
Thank you, sir. Thank you for the introduction. Is my screen audible?
Ma'am, your voice is audible.
Is my screen audible?
Screen also audible. Visible.
Screen is visible now?
Yes, ma'am. See. Continue.
So, good morning. So, it's morning 6:40 a.m. I'm now in Budapest, Hungary, not in Germany. So, it's morning 6:40 a.m. So, I was very curious to give this talk when Dr. Selva Kumar asked me whether I can give a talk, and then Dr. Stanley asked me whether I'm okay with it, and I said okay. And it's also an honor for me to give a talk to a Jesuit institute because I did my uncle from St. Joseph's College, Trichy. And so with this, I will just give my talk on the field-induced ordering in microgels. I think that most of you are all chemistry students, and most of you have studied physical chemistry, so I will just begin my talk with an introduction to colloids. So these are the colloids which you come in light, for example, milk, paints, all cosmetic items, detergents, surfactants, even most of the medical formulations. Now, what is one important property of colloids? They can scatter. So if you take a colloidal solution, say for example you have taken milk, very dilute milk, and then you have a solution with salt or sugar dissolved in it, and when you pass light or when you shine a torch in a dark room, you can see the light path in the milk solution, but not in the solution with sugar or salt. The same like early morning when you take a photo or something, if you see the small rays of sun, or in laser shows where you can see the very beautiful lights on the sky, it's all because of colloidal particles being present in the air, and they scatter light. And this amazing phenomenon is called as Tyndall effect. So now colloidal particles are being researched worldwide, not just for their applications but also to study them as model atoms. So if you take any colloidal system, the number of particles which are needed is around 10 power 13. Whereas in atomic systems you need 10 power 23, which is the Avogadro number of atoms. And when you see the elastic constants of a colloidal system, it is 10 dynes per centimeter square, whereas for atomic systems it is 10 power 10 dynes per centimeter square. As the elastic constants are very small, I ask all of you to pinch your cheeks. So what do you feel? They are very soft, right? This is because the elastic constant of our body, our skin, our muscles, everything is falling in the range of 10 dynes per centimeter square. And it is because of this reason our skin or like our eating, everything can be easily deformed. And this material, whose elastic constants are in this range, come under the topic called soft metal. So there are two topics. One is hard condensed metal, where most of the inorganic particles come into play, and there is soft metal where most of the polymer physics come into play. So my topic here will cover synthesis in chemical aspects, but studies on physical aspects. So basically I work in a system of gels. So a gel is nothing but a three-dimensional cross-linked network which is swollen in a medium. So for example, these junctions are called crossing points, and here I have marked these as polymer networks. And if you have If you have water as the dispersing medium, we call it as hydrogels. So the latest in hydrogel technologies, most of you are using contact lenses, and this is the very latest Apple iWatch, which has a hydrogel protected screen, and most of the wound healing patches are now coming with hydrogel as because it also offers you moisture around the wound. Then there are also organogels, aerogels, aerogels, metallogels, ionogels. These are all classified depending upon the medium in which they are dispersed. In organogels, if the medium is an organic solvent, then it is called an organogel. In aerogels, air as the medium, aerogels, nothing is there. Metallogels, if you have some metal ions, and in ionogels, if you have an ionic liquid being dispersed. So here I'm showing one of my research where we synthesized an organogel from polyanisopropilenacrylamide vinylpyridine, and this organogel has lot of applications such as it prohibits the growth of bacteria. It also uptakes lot of heavy metals like arsenic and chromium, and also dye degradation studies. It also absorbs most of the industrial textile dyes. So the system I work, I said it is a gel. So the name of the chemical molecule is polyanisopropilenacrylamide, and we can synthesize these particles through free radical precipitation polymerization. This gel is stimuli responsive. This means that, so if you see here, this is the structure of the microgel, and it is, I said it is a hydrogel, but it is also called a microgel, which I will tell you later on why it is called a microgel. Being hydrogel, it is dispersed in water. This means that it can form hydrogen bonds with the water molecules nearby. So when you take a dilute suspension of this colloidal particle and hold it in your hand, because your body temperature is around 37 degrees, in a few seconds, you will see that the suspension becomes turbid. This is because when it crosses a temperature of 34 degrees Celsius, the hydrogen bond breaks, and the isopropyl groups, which are here, come close by, and then it scatters more for the visible light. So this is a temperature sensitive gel. Now we can, as chemists, our unity is that we can make particles to our willingness. So we can make these particles into nanoforms, microforms, or even as big bulk microgel networks. Also, like a good cook is always a good cook. So if you are a good cook, you can make all these particles exactly of the same size, which we call as monodisperse systems. And when you get monodisperse systems, the phenomena you can study with these systems are amazingly remarkable. I said, like when you have a dilute suspension and when it crosses 34 degrees, it becomes turbid. It is only a physical phenomenon, but how do you quantify it? So here I am showing you a representative. It's not representative, it is an experimental plot of where we have taken nanogels whose size is around 273 nanometer at 20 degrees. And then when you increase the temperature gradually, the size actually decreases. And at this junction, you see that there is a graduate fall, and this fall is what we identify as the volume phase transition temperature. This is the temperature at which the hydrogen bond breaks and the isopropyl groups come in close proximity. So now once you have this system, what you can do with this system? So you know that in hard spheres, for example, most of you have studied in solid state physics or solid state chemistry, the most possible or the maximum packing fraction which is possible, that is the volume fraction, is 0.74. But these systems of gels which I am showing you here are quite different from those systems because you can go beyond the maximum close packing of 0.74. This is because the size is changing with temperature. So in any hard sphere system, for example, if you take polystyrene spheres or gold atoms, for example, the gold size doesn't change with temperature. So for every temperature, it's going to be the same gold atom size. It is not going to change size. So if you calculate the volume fraction, which is given as pi d cube by 6 into number of particles, the number of particles is fixed. D cube means the diameter cube, it is also fixed, diameter is also fixed. So for gold atoms, for polystyrene spheres, the volume fraction doesn't change. But in the case of gels, because every temperature you have a different size, your volume fraction changes because your diameter in the formula for volume fraction keeps changing. And then these particles are responsive to temperature. So initially I showed you that it is changing with temperature. So whereas depending upon the solvent is being dispersed, you can see that the particles can be swollen, they can shrink, they can also deform. They can even form facets, which I am not showing here. Another important aspect of these microgels is that we synthesize these particles by free radical precipitation polymerization, and once this oligomer radical keeps growing, after a certain concentration they collapse, and the collapsed particles have a dense core, and then there are dangling ends which we call as fuzziness. So, and these particles are generally represented not as hard spheres but as fuzzy spheres. In the upcoming slides, I am going to show you the results on poly N-isopropyl acrylic acid. So this is this part is temperature responsive, this is pH responsive. And so acrylic acid imparts a lot of negative charge to the polymer chains. So you can see that the zeta potential is quite high for the samples at various temperatures. And this is the diameter of the particles as a function of temperature, and it's about 1 micron. So when you have 1 micron size particles, means they are quite large, and what can you do? We can do some imaging. So here I am showing you a confocal laser scanning microscope. So this is a very nice microscope where you can image deep inside the samples, provided your samples are quite transparent. You can also get the various focal planes. You can go to the various focal planes and construct the 3D image of your sample. So most of you have studied about Brownian motion. So here you can see that. So these particles, the 1 micron size particles, are labeled with the fluorescent dye, which is based on rhodamine, and it shows the Brownian motion. And here you can see that I said that they are model atoms. That means they mimic atomic systems. So in atomic systems, the crystallization phenomenon is quite fast. So we cannot. So whenever you want to image gold crystallization or silver crystallization, it's a very fast process. It happens in picoseconds, and so you cannot image them. Whereas when you have larger size particles, you can model the system atomic phenomena. And so what you saw here is how the colloidal particles are assembling in real space. And so in this picture also, so these are only pseudo colors which you are seeing here, which just coming because of the dyes, and here you are also seeing the grayscale image. And we can also study a lot of in solid state chemistry. You might have studied about point defects, stacking faults, and also if you see, so this is another stacking fault, which is here you can see the plane is continuous here, and so you have a fault coming here. So this is kind of Y defect, and you don't have any particles here. So these are the point defects. You can study all atomic phenomena like Scotty, Frankel defects, but in a larger scale using colloidal systems. Next, we can also study, like if you have, so for example, I showed in the previous slide how atoms stack and form crystals, and when you have such crystal formation, you can study whether in which crystalline phase they exist. So for this, first we take the first plane and let us assume give it a red color, and then you move to the next plane in the confocal microscope, give it green color, and then move to the third plane and let us give it blue color. So if you have A, B, C kind of scattering, which is for FCC crystals, you will, when you merge all of the three images together, you will see all the three colors separately. Whereas when you have HCP stacking, the first layer will overlap with the third layer. That means you have an HCP ABA kind of arrangement. So here in this region I have imaged about 20 layers in the crystalline sample, and we find out what is the stacking probability, which is around 0.45. This means the sample is not FCC, not HCP, but it is a coexistence. Then for if some physicists are there, they may know about pair correlation functions. So pair correlation function is nothing but if you have a particle at a given origin and how another particle is related. So the first position tells you about the nearest neighbors, and the second position tells, and the second and the other positions, the peak positions tells how nicely your sample is arranged. So we see lot of peaks coming up. This means the particles are arranged in long range order, and these two peaks matches with that of our simulated data, and it implies that the particles predominantly exist in the hexagonal closed packing state. So now coming to the electric field studies, which is the main title of the presentation. So we take this microgel suspension, take a few microliters of it, put them in between a cover slip, and then apply electric field. Put these particles somewhere here in the microscope and study in the XY plane, XZ, XYZ, in the time and along the Z axis how the particle dynamics changes. So we applied an electric field strength of 100 kilowatts and then vary the volume fraction. So we take dilute samples to highly concentrated samples. So in a dilute sample, which is shown here, you can see that the particles are in a random motion, and when you apply field, you don't see much here. It's almost the same, but only the number density has changed. But here in this case of the next sample, when you the same, there is no electric field. Here the electric field is about 0.44. Is the screen visible? So if you see here, the particles are, you can see that the picture is quite different from what you see in the previous image. So here you can see the particles undergoing not Brownian dynamics, but a sort of arrested dynamics. And if you see the XZ plane, you can see the particles are arranged in the form of strings. So when you have microgels, putting in any colloids, not just microgels, if you put them in an electric field, they form dipoles, and dipole-dipole interaction leads to the formation of strings in the direction of the electric field. Next, we also came upon an interesting observation where we see that we could have sufficient concentration, the particles can form crystalline structures. So here you see the body-centered cubic arrangement of the particles, BCT. But in addition to it, what we saw is that the particles can also form rings. So if you take a paper and if you fold it and if you look it from the top, it looks like a ring. But essentially it is like a pipe or a tube. So what we see in the top surface is actually the ring. But when you see it in 3D, it is going to be a ring. So here you can see that they are actually rings in the 2-dimension. And here I have made the 3-dimensional reconstruction of about 20 planes, and you can see they are actually tubes. So this is my favorite part of imaging. So you see this image on your right is the particles before applying field. So now here comes the magician, and when I turn on the electric field, you can see what happens. See, they form very beautiful structures. So some forms VCT structures, some actually open up to form rings. So what is so important about these rings? Why? Okay, I saw some rings. Is there any value to it? Yes. So if you can arrest these tubes, you can study how muscle filaments are arranged in the body and what is their collective properties. So I said we are studying the collective properties of atomic systems. So you can study how in a carbon nanotube, how conduction takes place, how conductive properties originate. So without having microtubes with us, we can study those properties. And these tubes are also remarkably good in that they have a sort of shape memory. So now the field is on. This video a bit fast. So now I am turned off the field. You can see the particles slowly will disperse off. You can see they are losing their structure. They dispersed off. They lost their structure, and now again I am going to turn on the field. They lost it, and now the field is on. So you can see that they will come back. They have a kind of shape memory. So when the field is on, they come back to this. So they also have shape memory, so it is good that such kind of materials can be used like for self-healing, where once they lose their structure, they can recover back their structure upon removing the kind of stress which caused them to undergo the structure change. In other systems, we see the conventional things like they end up with body-centered cubic structure, and here you can see these are long strings which are in the Z direction, and this is the large-scale 2D imaging of how these particles in field behave. And then next, so what we saw so far was larger size spheres, so we used a microscope. Now we will have very small size particles, so I synthesized the particles of around 70 nanometer to 100 nanometers. And then, so for this particular experiment, I used 100 nanometer particles and then put them in a field cell, which we constructed for our neutron scattering experiment. So these experiments were conducted in the FRM2 KWS2 small angle neutron scattering facility in Germany. So we made, so you might have studied about neutron scattering in your master's classes. So first we determine the match point, and then after the match point we subject the particles to electric field as a function of concentration, and these are called as the form factors. And so we fit the fuzzy sphere model to the form factor, and so from the fit we extract the size of the particles. Now the same sample, all these concentrations have been subjected to field measurements, and so with electric field you can see how the profile changes. Interestingly, we don't see much change, only except the fact that with field the intensity of the scatterers are improved. Whereas if you come up to the higher concentration samples, you see that they develop nice structure profile here and they don't collapse onto each other. When I say they don't collapse to each other, you take the field value for all the concentration or the field values for a given concentration and normalize them, then you see that all the data collapse into one point. Whereas when you take the field values for the higher concentration, they don't collapse. When you see a normalized grain density not being collapsed in case of any scattering, that means there is some physical phenomena happening. So in our case, there is shape change. So I said that the particles can change shape. Here they change their shape and compress. So on very loosely cross-linked microgels, when you say loosely, so in my schematic diagram, I show cross-link points. When your cross-link points are very weak, then they become extremely soft. In such systems, we see that particle size can change from 180 nanometer to even 100 nanometers with the application of field. So we here see that they are not just responsive to temperature, pH, but also to field. So with that, I will shorten my presentation here on the results of the phase diagram. So this is the theoretical phase diagram given for ionic microgels. So we exactly see all those phases for microgels experimentally, but in addition to the theoretical phase diagram, we see here a new phase of tubes coming up. And then it has been from our group, we saw that spheres cannot form cubes because the energetically favorable structure for spheres is always the DCT structure. But in our studies, we have spheres and we see the tube structure, and at the moment currently we are investigating why tubes are formed in sphere systems. And next I will give you just a minute presentation on what I am currently doing in Germany. So we all might have seen this very smelly structures, which is a sewage treatment plant. And this plant is quite stinky and you always close your nose when you come across these regions. But let's see what is actually happening here. So in a sewage treatment plant, so the water comes on here, you remove all your, like some people even throw dolls, napkins, tissue papers into the flusher, and they are all filtered in this section, and other including your toilet, urine, everything passes over here, and then it goes to the primary clarifier, and the top part of the liquid moves on to the secondary clarifier, and from the secondary clarifier the water is treated and you get almost drinking quality water, but we don't use it for drinking purpose because humans are still not easily motivated to drink such water coming from sewage treatment plant. So for that purpose now this water has been used for agriculture purposes. So my work mainly focuses on this part. So I work in a company also as part of my project. So which is called as BTA, and so we have developed a secret formulation, and you can see that this formulation is so impressive that you can, so this water, brown color water, you are seeing actually toilet water, okay? So it's coming up, and so we added this liquid. And so you can see the action of this water liquid. Okay, so this sediments in 18 seconds, but it was a slow motion video for you. So we work on these systems, and I use polystyrene particles to mimic the systems and study how the kinetics of aggregation happens. So this is all about today's presentation. I would like to thank my collaborators Professor Peter and Laura, and to all my funders, and to the organizers. Thank you so much for having me here, and to the audience for listening to me. And if you have any questions, I am open to answer you.
Thank you, ma'am. Audience, if you have any queries, please rise towards that. At least she will be happy if you raise at least 1 or 2 queries. If there is no queries, thank you, ma'am, for spending valuable time with us. On behalf of our organizing
Thank
committee
you so much.
and all the participants, I wholeheartedly thank Dr. Brijitta for spending valuable time with us. Thank you, ma'am. Thank you. So we move into the next technical session.
Thank you so much.
Thank you, ma'am. Thank you. The speaker is Jenn Anand, Process Engineering Manager, Department of Plasma Dry Etching, Intel Corporation, Arizona, USA. And the session will be handled by Chairperson Dr. C. Maria Magdalene, SXC Palayamkottai. I hand over the session to Dr. C. Maria Magdalene.
Respected professors, my dear participants, dear students, a very good morning to you all. I am very happy to stand before you to introduce our the session speaker, Dr. Jenn Anand Sundararajan. Is engineering manager in Intel Corporation, USA. His education, initially he did his BE Mechanical Engineering in India. After that he moved to USA for his higher studies. He has completed his MS in Physics, PhD in Physics in the University of Idaho, Moscow, USA. And his work experience, he was holding various posts in many institutions. Initially, he joined as a software engineer in Cognizant Technology Solution India. He was working from 2006 to 2009. So after 2009, he joined in University of Idaho in a different position, like teaching assistant and web author. He was there till 2014. So after 2014, he joined an Intel Corporation and serves in various positions like process engineer, group leader. At present, is engineering manager in that same Intel Corporation, USA. And also is a good researcher. He is having many publications in various international journals. And also he is a reviewer in many journals, and also he is a research collaborator, and he also received many research awards. With this small introduction, I welcome on behalf of St. Xavier's College, on behalf of all the participants, to Dr. Jenn Anand. We welcome you, sir.
Thank you very much, madam, for giving a very warm welcome. Appreciate it. Let me see if I can share my video too. Is my voice audible?
Is that it is audible?
Okay. Okay, great. Can you see my screen too?
Is that easy?
Okay. Awesome. Perfect. Thank you. Good morning. So, wanted all gathered here this morning. I first of all would like to thank everybody in giving me this opportunity to talk about my research, a portion of my research. I also like to thank Professor Yanakumar from MKU who reached out to me to give this talk. Without further delay, I would like to get into my talk. I currently work as an engineering manager at Intel, but I'm here to talk about radiation effects on magnetic nanomaterials and its application in nuclear energy. Okay. So we'll talk about the motivation of this research this morning, first of all, and then we'll move on to talk about nuclear reactors a little bit and how these magnetic nanoparticles play a role in nuclear reactors. There are several challenges that we face today in nuclear reactors, and how these nanonuclear materials are going to help sustain these nuclear reactors in the future. We'll talk about that. And specifically, my area of focus is magnetic nanomaterials. So what I will do is, I'll talk about the magnetic nanomaterials, two types of nanomaterials I'll talk about today, which is fully oxidized nanoparticles and then coarser nanoparticles, and how these two play a role when it comes to understanding nuclear radiation and its effects. Okay, when you think about energy resources, there are so many energy resources available in the world. Some are renewable, and like wind, water, sunlight, food. Of course, we need food to survive. There's also fossil fuels, right? Oil, coal, natural gas, and then we have nuclear fuels as well. One drawback of using oil, coal, natural gas is that it's going to negatively impact the environment. So we need to have some sort of clean energy, and that's when nuclear power comes into the picture. Of course, wind, sunlight, and water can also play a vital role, but we haven't moved to a place where you can survive and sustain the energy for a huge group of people. So currently, coal, which is one of the fossil fuels, natural gas, and petroleum. Very few percentage of the energy is being used in renewable energy. And then we have nuclear energy as well. But we have a lot of scope for this nuclear energy in the future. If you think about the world population, by 2050, we'll hit like 10 billion people on this planet. When we have more people on the planet, what does that mean? We need more energy, right? We need more people. As we have more people, we need more energy. As we can see, kids these days use so much of gadgets, right? We have electric cars. Everything is electric. Everything is mechanical. So we need a lot of energy to survive in the world and to sustain the world as we know it. We think that's where the nuclear power comes in place, because it has a lot of potential to give energy to help us sustain. If you think about the nuclear fuel cycle, what they do, basically you mine for the nuclear fuels, uranium dioxide, and then you mill it, and then you enrich the uranium fuel, then you make the fuel fabrication. Basically these fuels are made into small pellets, and then they are supplied to the nuclear reactors where they burn, where they go through nuclear fission, right? Nuclear fission reaction, and then they give energy to us to provide electricity for everybody. But we have spent fuel, and that has to be stored somewhere. But in each of these phases of the nuclear fuel cycle, nanomaterials play a role. Right from mining, all the way till recycling the fuels, we see nanomaterials playing a vital role. Today, my focus is on the nuclear reactor, mainly because what happens over the course of time in nuclear reactors? Materials fail, right? This is the inevitability of life. We all go through this, right? Everything breaks eventually. Everything is destined to die. Everything decays. Likewise, materials also eventually break down, and when it is in a very highly radiative environment, because it's being constantly hit by neutrons, what happens? These materials eventually fail. So we need to have some materials that are able to withstand radiation, that can survive in these harsh environments, and that's where nanoparticles comes in place. And the technology that we are going to utilize to help these materials survive longer is called the nanonuclear technology. Basically, we are going to use the nanomaterials, nanoparticles, nanowires, or whatnot to put in these materials that are at the core of the reactor so that they can withstand high radiation and fatigue and withstand fatigue or damage. Okay, that's my main focus. I think the nuclear reactors right now, the majority of the nuclear reactors in the world are coming to an end, right? They have their own life. Everything has its own life. They're coming to the end. We need to come up with a new reactors which can survive in this harsh environment. You know, it should have such a design that it can withstand, not just fall away or fall apart over the course of time. It should survive in the future. So when you think about nuclear energy, what comes to your mind? You know, the moment when they said that, hey, we're going to put a nuclear reactor in Tamil Nadu at the corner near in Kanyakumari, you know, everybody was like, no, 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 we cannot do that. Why? Because it's going to explode, it's going to create so much of radiation, it's going to impact people. There's so much opposition, right? The threat is real. Honestly speaking, of course, nuclear reactors, if they fail, they're going to cause safety issues. You know, not only that, it's going to impact a generation of people, right? So we need to create nuclear reactors. So performance and safety is definitely a challenge. The other one is waste storage. Of course, there is no harmful gases or greenhouse gases that is getting released to the environment to cause ozone holes, but in fact, there are nuclear waste that is being generated, spent fuels. These needs to be stored somewhere, right now we store in mountains and all the other places there, but eventually we are going to run out of this place. These are nuclear radioactive material which can decay for years, thousands of years, right? So it's going to impact the future. So those are the two main challenges. And we need to, my focus is mainly on the safety and performance of the nuclear reactor, how we can make materials that can survive in this harsh environment. We know about several things, Chernobyl reactor which exploded, and 3 Mile Island incident, and the Fukushima Daiichi, Japan, when the tsunami happened, right? The nuclear reactors failed and impacted the environment. So that's the focus. Let's try to create some materials that are able to withstand harsh environment. What happens when a material is exposed to radiation? What happens is, actually, Dr. Brijitta also touched base a little bit about that. There are voids that gets created eventually on the materials because the atoms gets dislocated from its site, and when the atoms get dislocated, it forms vacancy. Eventually, these vacancies join together to form a void, as you can see in the picture. The white spots indicates voids. And what happens when the voids form in course of radiation? The voids can get together, and it can cause the material or change the material to be more brittle. And when the material becomes more brittle, it's going to crack, and eventually the materials will fail. And this happens all the time. And we need to change the materials on time and stuff. So that's why we are doing these research. And this is a fuel clad, this is how the fuel clad looks inside the reactor. These are fuel pellets, like uranium fuel pellets. And this has a surface alloy, the outlet. And over the course of time, you can see it gets oxidized, and also it starts to form voids when it's subjected to radiation, and eventually it will break. So these are real issues you face in reactors. So let's get back to the basics now, right? Let's take 3 atoms here. And what happens when it's exposed to radiation, right? Radiation and its interaction with matter. So let's take an energetic particle, either an ion, neutron. It can dislocate an atom, and it can cause vacancy, or it can the dislocated atom can fall in between the cells in the lattice and form self-interstitials, right? This is a vacancy right here. And the vacancy, the number of vacancy formed depends on the energy of the particle that is hitting, and also the weight or the mass of the atom that is present at the lattice size, right? So we have a mass, two masses here. As they collide, it causes elastic collision or inelastic. It causes inelastic collision and as elastic collision, depending upon the weight of the material, and then it can eventually lead to the displacement of these atoms. And we can calculate all of those depending on the weight, the weight, the energy, and all of that. So how far these atoms can go and stuff. Okay. What happens when the electron is dislocated from its site? So it gets ionized, right? Electron energy disposition happens, it gets ionized, and it forms charge on the material. That's one effect. There's another effect, which basically is causes the atom to vibrate in its lattice side, and as these vibrates, it produces heat. And what happens when heat is present? It's gonna diffuse these atoms and causes several other secondary defects in the material. So it can form different cascades, it can form voids, it can form dislocation loops. A whole plane of the atom can be dislocated. A whole plane of atom could be missing there. And it can cause so many intrinsic property changes within the material. Okay, and it can cause vacancies and voids, which eventually leads to embrittlement and the material failure. So this is the basics of the radiation interaction of the matter. This is where nanonuclear technology comes in, because we're going to use these materials to actually minimize these effects in terms of formation of voids or vacancies. We want to minimize as low as possible. So we are going to use the nanomaterials, nanoparticles, and use it in these stainless steel materials used in engineering. So here is a picture showing how the tensile strength of the material is improved with the dispersion of particles. If you just take a plain stainless steel, this is where the tensile stress is. But if you take the oxide dispersion strength, then basically these are yttria oxide dispersed throughout the stainless steel, its tensile strength is even better. But if you increase the nanopheritic alloys, which means nanoparticles dispersed in the stainless steel, then it's going to even further increase its strength. What is happening here? The underlying principle here is, as the particle size gets smaller and smaller, it's going to create more surface area. More the surface area, more the grain boundaries, more the interfaces. And these grain boundaries and interfaces play a key role in dissipating the defects, in kind of suppressing these defects. Okay, so that's the main principle behind this. So there is a scope for nanomaterials. And here is an example showing the advantage. The top picture shows particles dispersed throughout stainless steel. The bottom one, here you can see there is no particles displayed. That's before radiation. After the radiation, what happens to the materials with the particles? There is very less voids. But what happens to the material without any dispersion of particles? It starts to form voids eventually, and eventually it cracks down. So the strength of the material is actually better in the oxide dispersed material, because void swelling is very, very low there. Okay, and we study magnetic properties because the magnetic properties shows something intrinsic about these materials, right? Whatever happening inside the atomic level, we want to know it. We want to sense it. We can't see it at atomic level, but magnetic properties helps us to look beyond, right? Helps us to give that insight. And then we are using ion irradiation because we cannot use neutron irradiation. The reason we cannot use neutron irradiation is because it's going to be radioactive, we cannot handle the material and cannot study. So we want to use ion irradiation, which is equivalent to a heavy neutron irradiation. As you can see from here, the efficiency is pretty much the same. So we use silicon ion just to replace the neutrons and to avoid radioactivity here. Okay, so our approach is to create nanoparticles, expose it to radiation, but characterize it before and after. it's pre-post irradiation of these nanoparticles. Let's do an apple-to-apple comparison to see how it actually behaves, how the structural property, magnetic property, intrinsic properties have changed over the course of time. Okay, advantages of in situ method. We also do in situ method because in situ is as it happens, right? We want to see how the structure changes. So we want to see real-time data. So that's what we're doing here. And then ion irradiation on ion-based ion-based nanomaterial. So like I mentioned before, we are using two types of nanoparticle types. One is fully oxidized ion particles, as you see on the left side. The other one is core shell, which means it has a core ion and the surface is all oxidized. So we take these two particles and then we create a thin film of nanoparticle film, and then let's expose it to radiation and see. One thing you can see right off the bat is, you can see here it has more grain boundaries, like you can see from this picture, these are grains, you can see how atoms are aligned in one plane, and there is an interface as well. But when you look at the fully oxidized nanoparticle films, it's either single crystal or it's multi-crystal, but there is very less grain boundaries and there is no interface pretty much. So let's have that thought in the back of the mind. And then nanocluster deposition system. So this is our deposition system that we use to create particles. Basically, we sputter these particles, we aggregate in the chamber and allow it to deposit on the substrate, and then it forms the fully oxidized nanoparticles. And this is a picture showing how the particles are looked. This is monodisposed particle. Pretty much the size is very uniformly distributed. You can see the bell curve here, narrow distribution, pretty much all having the same particle size. And this is how it looks in the cross section on the substrate. This silicon sulfate deposit particles, you cut it, this is how it looks on the right side. Like I mentioned, we are studying the magnetic property. Basically, we take a material, we expose it to a magnetic field, and it's going to retain some of this magnetic property, right? And when you remove the magnetic field, it still has its remnants. That's what happens when you take a magnet and we can put it together with a nail. The nail still has some magnetic properties in it. That's the remnants. And then after the amount of magnetic energy that you feel that you need to apply in the opposite direction is called as the magnetic coercivity to remove the magnetic field. That is what it is. So radiation setup, we activate the ions, use the magnetic protocol to focus the ions, we radiate on the sample. We basically scan through the sample. Okay, enough of what or the preliminary setup, right? Let's go into some data and look at what we have here. So like I mentioned, we are studying two types of particles for nuclear energy applications. One is fully oxidized nanoparticle films. And that's what I'm showing here. Iron oxide, right? Fe3O4. And these are granular films, and these are exposed to heavy dose of silicon ion, right? And it's like 10 to the power 16 ions per centimeter square. So heavy ion irradiation. And the blue hysteresis look here shows that they are unirradiated. After the radiation, this is how it looks. So what has happened? Before irradiation, it was basically paramagnetic, right? And after irradiation, it became ferromagnetic. Basically, it started to gain some magnetic property in it. So there is a huge change that is happening for the ion oxide material. And we will take a look at the XRD image, the XRD spectrum here. What we found is the grains have grown huge. You can see the unirradiated films are only 3 nanometer size, but after the radiation, the grains have exploded pretty much, right? 7 times or 8 times more. And you can see it's like 23 nanometer here. And we can see from the thin peaks here that the grain size has grown drastically. So there is a huge change that is happening here in the radiation. Let's take a look at the surface morphology. This is how the unirradiated film look like. But after irradiation, you can see everything is conglomerated together. They kind of agglomerated together, and there is a huge change that has happened. Taking a close look at the magnetic interaction using the AFM studies, this is how before irradiation the particles look like, and there is no magnetic interaction here from the MFM. But after radiation, you can see the particle size have grown huge, and also you can start to see magnetic interactions happening between the sites. So irradiation did something to that, and what did it do? That's what we want to find out, right? Yes, of course, this is great. There is a magnetic interaction, but I want to know what exactly happened. That's where curiosity kicks in, right? As scientists and researchers, you young minds also will need to start questioning why things are happening the way it is happening, right? You want to question and find out the truth. So just a summary here is like before radiation, it was very small grain size, but it has grown a lot. And then it was not magnetic, so paramagnetic before, and now it is ferromagnetic now, right? And there's a lot of things, aggregation has happened. So this is the phenomenon that actually has happened. When we saw the basics of radiation, basically the electrons, when the ions hit the atoms get dislocated. And as they get dislocated and heat kicks in, slowly start to migrate and form bigger grain boundaries. So you can see radiation and grain growth. The fundamental thing that is happening at the underneath is basically the migration of atoms from one side to another side. So it's called the mechanism of grain nucleation that is happening inside the material, and that is causing interaction. Then aggregation also happens at the outset because these are small particles, very fine particles. They aggregate together, coalesce together, that's the method of osmotic ripening, and form bigger particles in here. And that's what we see here. As you can see, this is the in situ study result. As we expose it to more radiation, they agglomerate together. There was no magnetic interaction before. Every single spin of the electron, the angular momentum is facing in a different direction. But after the interaction of ions and radiation, now it's becoming ferromagnetic, and there is a magnetic interaction overall. And when you apply a magnetic field, everything aligns together perfectly, and also it is able to retain the magnetic field for some time. So, structural growth and magnetic interaction, right? Both has happened, and eventually particles aggregate together. Let's take a close look at to see, hey, I irradiated the sample, I know electron radiation, there could be some ionization that could happen, right? Because we are talking of some electrons. Could that have played a role in that? That's what we find out here. And as you can see, any amount of electron radiation, the particle size, the structure did not change. This is an in situ study here. So electron radiation, although has some contribution to heat, it did not have a high contribution to the agglomeration of the particle. So we can easily eliminate electron radiation. So we're going to break things down, right? Electron. It's not the suspect, it's excluded. Let's go to the next one. What about the thermal effect? Because you mentioned that there is temperature, there's going to be diffusion, there's going to be agglomeration, there's going to be coalescence of voids and stuff. What about the thermal effect? And if you just purely expose thermal, there is no change actually happening, because even up to 773 Kelvin, there is no agglomeration or no change in physical properties of these nanoparticles. The only time when any agglomeration or mechanical interaction starts to kick in, then we actually irradiated with heavy ions. And we actually started just with the helium ion, starting with the lowest and the lightest ion here, helium, and we can start to see it start to change structure and stuff. So, in the end, what we can conclude is, yes, there is electric collision happening. That is the major contributor for the grain boundary evolution and particle agglomeration. The next one is the thermal and electronic process do not directly contribute to anything, but they do contribute one at a time, slowly in terms of heat. That is all we want. So we took oxide particles, we exposed it to radiation, We saw structural changes. We saw the magnetic properties change drastically. Now we have an understanding that this is happening due to the elastic pollution aided by ion radiation and grain growth. Thermal and electronic process could have contributed a little, but not the ultimate contributor. The next particle that I'm going to talk about is the core shell, because it has iron core and oxide shell. Hold the thought on the outside, and well, let's see what happens here. Here you can see, because of iron core, it stayed ferromagnetic, and after the radiation also, it stayed ferromagnetic, so no big change. And even the grain size has not grown much, but only the oxide shell grain size has grown a little bit more, from 2 nanometer to 70 nanometer. So the core is retained and it's preserved even with the high dose of radiation here, as you can notice. And how the structure looks like, it's an irradiated film, and you can see the irradiated film looks like a uniform film, with you can see still the core particles. The core is retained. This shows that the material is kind of very robust or stable to irradiation because of the core shell interface effect and grain boundary effect. That's what I want to talk about, because the core is retained, and we know that this has a lot of grain boundaries, and also it has core interface effects. So if you look at the outset, this is what has happened. Eventually, this outside structure changed from Fe3O4 to FeO, but the core is still retained because there is no change in the core, and it starts to form something like this on the material, as you can see from the picture here. So one thing about the interfaces, let's take two different materials. We have erbium and copper. When you expose it to radiation, what happens is it forms a huge number of defects. This is a simulated one, and it absorbs. This is from a different study, and eventually everything disappears. This is like 2 picoseconds after cascade, really short period of time. So the interface plays a huge role, right? And as you can see, the iron core has a core and an interface, iron oxide has an interface. So that tells that these interfaces could act as a sink, because the interface always has pre-existing voids where these defects go and settle. They act as a sink. So quick annihilation of radiation defects can happen if you have interface, if you have grain boundaries. That's the best to have a radiation tolerant material. And grain boundary effect, the same story here, because the grain boundaries can act as a trap of voids, trap of vacancies. It can even dissipate some of the dislocation loops. So grain boundaries play a huge role in actually minimizing the radiation-induced defects. And what does the core shell nanoparticles do? Because it has a core, it has a shell, it has interface, as well as it has multiple grain boundaries too. Here is a study I want to show. It's a very recent study from 2020, and it shows how the particles have under irradiation behave. As you can see, these particles have a core and a shell. That's a surface, and these are polycrystalline, right? From the study, you can see it's polycrystalline. Multiple lines you can see here. It's polycrystalline, and you can also see that these particles have some pre-existing voids in the interface, and that could act as sink to help dissipate these voids that created under irradiation. So as we expose it to constant irradiation, you can see what happens every 5 seconds, or 10 seconds. This is as it was prepared, and then after 5 seconds of radiation, you can see a lot of voids. But immediately, in about 15 seconds, you can see the voids start to, or a lot of vacancies of the defects start to disappear. 20 seconds, 25 seconds, 30 seconds, 35 seconds, 40 seconds, you can see it forms and dissipates, forms and dissipates. That's a constant action that happens because of grain boundaries, because of interfaces. And these are stainless ST nanoparticles, and this one shows the loop density, basically dislocation loop. The dislocation increases immediately, as you can see from the picture, but then it eventually dies out completely. But if it's just a foil, not a nanoparticle, you can see it just keeps going up and up, and it forms voids, small voids. So this is a good study, telling that it supports my study as well. That the presence of interfaces and grain boundaries actually helps in distributing defects. So in the end, what do we have here? Our objective is to create materials that can withstand irradiation, right? So we went ahead and pursued two types of nanoparticles to understand how each of them behave under radiation. Our ultimate goal is to use these nanoparticles, disperse them in stainless steel, and study how they behave. At the end of the study, what we have here is, we have some materials that are very sensitive to radiation, right? They could change the structure drastically. But if there are interfaces and grain boundaries, even with high temperature, even with a high dose of radiation, they can still survive and sustain, throughout the radiation process. So we need more nanoparticles being used in nuclear reactor materials. And also, sensitive materials can be used for some sort of study where we can know what is the radiation dose, what is the radiation sensitivity, and all of those things. So, no data is bad data, right? Whether we succeed or not, even if we have the data that is not unpleasant, that is not what you expected, it still tells a story. And for you young minds, it's a great message too, that when you don't get the data that you want, don't get disappointed. No data is waste data. It tells something. 1,000 times you might fail, but 1,000 times you learn that this is not the way you need to try. You need to try in a different way. So that's the positive note. So we have a candidate for radiation tolerant materials as well as radiation sensing materials too. There is more opportunities here. Whatever we have went through today is just only skating through the surface of the iceberg. It's just the tip of the iceberg. There is a huge, study that is waiting for people to come explore and find out and contribute to the nuclear energy here. And today we touched base on the materials of the nuclear reactor and how we could improve its quality and resilience. But there are so many things from mining, forming nuclear fuels, nuclear waste separation, and also you can use it to capture some of the fission reaction byproducts to use it for future, applications too. So there's more areas that needs to be explored in this particular field of study, and you have an opportunity if you guys are interested in that. That's the end of my talk, and now open for questions. If you have any questions, please feel free to shoot them now.
Thank you, Dr. Jenn. Participants, you can raise your queries. Yeah, students, the goal is on your side. Anybody? At least one student. Research scholars, many of the research scholars are going to give oral presentation also. Please raise at least one question. Okay, I give this to Dr. Gurunathan.
Okay, yeah, go.
Actually, I'm not expert in physics, so my question is, am I audible?
Sorry, your voice is not audible. Sorry about that. Can you say that again?
Can you hear me now?
Yeah, I can hear you now.
Yeah, my question is stupid because I'm not expert in physics. In nuclear reactor, the fuels are used in broad form. So I wonder that, if the nanomaterials are, they are in powder form mostly because surface matters.
ಸುರೇಶ ಜೀವ ಜೀವ ಅಂತಾರಲ್ಲ ಅವ್ರ ತಂದೆ ஞானகுமார் யூனிவர்சிட்டியில இருக்கார்ல மதுரை காமராஜ் யூனிவர்சிட்டியில சென்ட் சேவியர்ஸ் பாளையங்கோட்டையில டாப் கொடுக்குறாராம். அதுல ஜூம் மீட்டிங்ல ஜாயின் பண்ணுங்கன்னு சொல்லி.
Okay. Sorry, I couldn't. Can you say that again? You're talking about some surface.
Did you get my question?
No, sorry about that. There was so much of noise. Can you repeat it again, please?
Reactor, the fuels are used in rod. Hello?
Yeah, go ahead.
In
Sorry,
nuclear
I can hear
reactor,
you now.
the fuels are used as rods. Whereas in nanomaterial, mostly they used as a powder form in order to have more surface.
Oh.
So how you are going to
I
use
see.
this to for real-time
Oh,
application?
yeah. That's a good question. We can actually create these nanoparticles, dry nanoparticles. Also, we can disperse in the solutions. Now, how we are going to disperse in the stainless steel is a good question. I have not personally done it, but we have also dispersed nanoparticles that have been used in stainless steel. I need to check the process actually of how they do it, but I am sure at one phase, as they melt these materials, probably they could disperse some of these nanoparticles inside. But now, how is the materials integrity is going to survive at this high temperature is a matter of question, right? It may be difficult. But that could be something the engineers will have the answers as they manufacture these materials. But there have been research in the past that have done and proven that oxide dispersed particles can be dispersed in these stainless steel materials.
Thank you. I have one more question.
Go ahead.
This iron oxide particles, in terms of energy, how efficient they are in comparison with uranium oxide or thorium oxide, which are really used in reactors?
Yeah, uranium oxide is mainly the fuels, right? But the iron oxide that you're going to use, on the structure that covers the fuels. So we're going to cover this uranium pellets inside these fuel cladding. So we're going to use the iron outside of the pellets. So it's not going to mix with the uranium oxide.
Okay.
But the interaction between that
uranium oxide and thorium oxide.
Yeah. Say it again.
Fuel, still the fuel are going to be uranium oxide or thorium oxide. So you only cover the surface.
Fuel will be uranium oxide only, but the material that is surrounding the fuel will be having some iron oxide material in there. It will be stainless steel typically or zirconium alloy, but we are going to disperse some iron oxide on that.
Okay, thank you for the nice clarification.
Yeah, no problem. Any other questions?
Any other queries? Yeah.
Good questions.
Good morning, sir. Sir, it's a different topic we have had. So I have one doubt. What is the preferred methodic preparation or synthesis of steel nanoparticles? And one more question is, what is the ratio of the iron maintained here? Whether it is maintained in the same as in the alloy or different ratio you are maintaining?
A good question. So the preferred method for our lab, we used the aggregation technique. We basically sputter the target, aggregate it together in a chamber, and then create them. So with this method, we can actually create monodisperse particle, which is like a uniform size distribution. But is this going to help us for mass production? Absolutely not. This method that we are using in the lab to create these nanoparticles of uniform size cannot work for mass production. It's going to basically massively fail if you do like that. But we have chemical methods which can create nanoparticles, self-assembled particles. We can create it at mass volume. The size may not be uniform, but more research is being done to create uniform size particles. So, if you are going to create masses for huge application, yes, we can use chemical methods to create this one. That's the first question. But now the second question is if you're gonna what is the ratio, right, Brian? Typically, majority of the stainless steel has iron, and then nickel, and then those chromium and other materials to prevent the oxidation of the material. But we are not going to touch the stainless steel composition there. What we are going to do is we are going to create some iron oxide nanoparticles through chemical methods, and then take it and disperse in the stainless steel material. So, irrespective of the stainless steel composition, irrespective of the material that is going to be used, it could be a zirconium alloy, it could be a stainless steel alloy, or whatnot. We are going to take these nanoparticles and disperse them. And this could be an opportunity to study for future, because we want to study how these nanoparticles behave under for different grades of stainless steel. So that could be the next study can open doors for that. I hope that answers the question.
This may be the last question. We are running short of time.
Sir, shall you explain how Fe3O4 core shell is formed?
Okay, that's a very good question. So, what we do is we sputter these, but actually I can go back to the slide here to explain. Basically, when we create these nanoparticles, we sputter it. Okay, here is the image that I want to show. So this is the target iron, and then we sputter it, and it causes the iron atoms to be released from the target. And as they travel, here is a pressurized chamber, they aggregate together to form the nanoparticles. This nanoparticle doesn't have any shell, it's just pure iron. But as they come and deposit here, what we do is we release some oxygen into this deposition chamber. And as oxygen comes into the deposition chamber, iron gets oxidized, right? And only the surface gets oxidized. Once the surface forms a protective layer, no oxygen could diffuse further. So it has a core, and now it also has a shell. But if the particles are too small, let's say 5 nanometers, as it oxidizes, the core also oxidizes, consumes, and becomes a fully oxidized nanoparticle. So the answer to your question is the size of the nanoparticle. Basically, if it's too small, it will become fully oxidized nanoparticle. But if it's enough size, then it can form core-shell particle like this. But how are you going to control the size? That comes to power, the gas supply, the amount of ions or particles that is getting released from the chamber to form these sizes of nanoparticles here. Good question.
Thank you, sir.
Yeah.
Thank you, Dr. Jenn. I hope
Thank you.
it's midnight in the US. Okay. Thank you, sir, for spending your valuable time with us. Thank you, sir. Thank you. Good night. Have a good sleep now. Thank you. Now,
Thank you very much for the opportunity.
Now, a few announcements. We are already running short of time. Now we have the tea break. You join the session immediately after the tea break. At least you take 10 minutes. 11:35 will be here. Okay. And one more announcement for the oral presenters. We immediately start the oral presentation in the first BSc chemistry class. So our students, please guide them to the first BSc chemistry class. Oral presenters, please go to the first BSc chemistry class. So we are going to immediately start the oral presentation. Through those who joined in the offline mode, please go to the first BSc chemistry class. So now the tea break. Please assemble here after 10 minutes. 11:35. Next talk is Dr. Kalyana Sundaram and Dr. Ranganathan. Okay, we are already running short of time. We should finish the 2 talks within 1 o'clock. They are also going to catch the train at 2 o'clock. Please understand our situations.